We talked about the OSI model, but did you know that the four-layer TCP/IP model started its development before the seven-layer OSI model was created? You see, what happened is that TCP/IP had too much momentum to be overtaken by the OSI model, and the OSI model was never actually implemented. However, we use the OSI model, that seven-layer model, as a reference model today. Now, the TCP/IP model is now what's dominant in today's internet, enterprise networks, pretty much everywhere. Now, we refer to the TCP/IP model as a protocol stack or a protocol suite, and so those names would be interchangeable. We also call it the DoD model. Now, that would stand for the Department of Defense. So here's what happened. The OSI model's development started in the late 70s, and it was published in 1984. Now, there was a network called ARPANET, and this was sort of the precursor to the internet. This was developed in the late 1960s. Now, ARPANET stands for Advanced Research Projects Agency Network. Now, Landmark Packet Switching Network, established in 1969. ARPANET was developed in the 70s by BBN. It was funded by ARPA, and then later that became DARPA, the Defense Advanced Research Projects Agency. And eventually it became what we know today as the Internet. And it was in the 90s that that name, ARPANET, was kind of deprecated, or we no longer used it. Now, in May of 1974, CONNENSURF published a paper that was called A Protocol for Packet Network Intercommunication. And it talked about the ideas that would be used later on in the TCP/IP model. March of 1982, the Department of Defense declared TCP/IP to be their standard for any computer that was used in military networking. And then January 1st of 1983, the ARPANET switched from the old networking protocol to TCP/IP. That old networking protocol was called NCP, the Network Control Protocol. So again, TCP/IP became the dominant networking protocol. Now, TCP/IP, as we said, is a protocol suite. And so TCP/IP doesn't just include the TCP, Transmission Control Protocol, and IP, Internet Protocol, but there are a number of other protocols that are specified as being part of the TCP/IP stack. Those protocols include the User Datagram Protocol, or UDP. It would also include ICMP, the Internet Control Message Protocol, and a number of others. There's applications that are part of the protocol suite. They're used for email, terminal emulation, file transfer. So again, this TCP/IP stack, or this protocol suite, it defines a number of areas of what we use today in internetworking. So if we were to look at the OSI reference model, that seven-layer model, we could see that it sort of lines up to the TCP/IP stack. The TCP/IP stack is a four-layer model, and it includes from the top down the application layer, which maps across to layer 7, 6, and 5 of the OSI reference model. The next layer down would be the transport layer. That maps directly across to layer 4 of the OSI model. Next would be the internet layer. That maps directly across to the network layer. And then we have the link layer, and that would embody both the data link and the physical layer of the OSI model, layers 1 and 2. So this is the comparison of those two models. We can kind of put off the OSI model and focus specifically on the TCP/IP stack. Now, there are certain application protocols that fall into that top layer of the TCP/IP stack. Applications that are used for email, for example, SMTP, the Simple Mail Transport Protocol. And then we have protocols that fall into the transport layer. An example of that would be TCP or UDP. Now, TCP is a transmission control protocol. It's used for reliable connectivity. UDP, on the other hand, is the user datagram protocol. It doesn't provide any reliable services. But either one of these protocols are used for communication, and they speak directly to the application processes that are running on my host devices that are on the network. Now, the internet layer, again, lines up directly with the network layer of the OSI model. With the OSI model, we said that the network layer was responsible for logical addressing. Well, that's the same with the TCP/IP stack. That logical addressing that we use would be the Internet Protocol, or IP. And we currently are using IP version 4. We represent those addresses as 32-bit dotted decimal addresses. We also have IP version 6, and that is an up-and-coming sort of protocol that addresses the scarcity of our IP version 4 addresses today. And then finally, down at the link layer, we also might call this the network access layer. Again, this combines both physical and data link layers of the OSI model, so not only does it deal with the physical connectivity and the voltage and so on, but it also deals with the service that the data link layer provides, which is access to that media. So those are combined down here in one single layer known as the link layer. Now really, if we were to just compare the OSI reference model to the TCP/IP stack, the big difference between the two of these is that the TCP/IP stack combines the top 3 layers of the OSI reference model. So all of that functionality, the service to the application that sits outside of the reference model, the translation of your data formatting into a common method that we saw at the presentation layer, the session services, those are all handled by an application protocol in the TCP/IP stack. Again, SMTP would be one example, and so on. Down at the bottom, we have the physical and data link connected. That's another difference between the two models. But really, if we want to compare these, here's what we say. The OSI reference model is just that. It's a reference model. And it defines some modularity. And then the TCP/IP stack, while it aligns with it, it encompasses its own entire protocol ecosystem. Now, there have been variants of the TCP/IP model. We saw the IP version 6 and IP version 4 that has been developed. But again, the TCP/IP stack is, again, a modular 4-layer stack. Within the TCP/IP model, we still have encapsulation and de-encapsulation. So you might imagine that you're going to send a request from your web browser to a web server. When that happens, you're going to send an HTTP GET request. Now, HTTP is an application layer protocol. Remember, we said that was handled in the TCP/IP stack in that top layer called the application layer. So that HTTP GET request is encapsulated inside of a TCP header. That TCP operates at the transport layer, and the transport layer still provides a service to the layer above it, which in this case is the application layer. So that GET request is encapsulated in TCP, which handles reliable connectivity. It then receives a service from the internet layer, which is logical addressing and path determination. So we put an IP header on there. The next thing that happens is we go down to the physical link, where an Ethernet header is placed on the entire segment of data here, the entire packet. It is then transmitted across the wire, and as that packet is transmitted across the wire, again, de-encapsulation takes place. It comes off of the wire. The Ethernet header has a field in it that says this is IP traffic, so we strip off that Ethernet header, and then we pass what's left up to the internet layer. The internet layer then reads the IP header, which has a field in it that says this is TCP traffic, so we strip that off. We pass it up to the transport layer. The transport layer has a TCP header that has port numbers in it, and the port that is in the destination field is port 80. Port 80 defines that HTTP application protocol. So TCP strips off that TCP header and passes this HTTP GET request up to the session at port 80, which is my web server. That's an example of how encapsulation and de-encapsulation works. If we were to go back down the protocol stack, we do the exact same thing. Each layer provides a service to the layer above it by adding a header and then passing it down to the next layer so that we can transmit our data.